Okay, good evening, or good morning, class. We're going to be doing Lab 44, Part A, Conservation of Energy and Application to a ramp problem, also a pendulum problem. So let me go ahead and we're going to start with Part A, which is the pendulum part. And we will be applying the conservation of energy in its full form to various scenarios. Okay, anyways, before we start, can someone tell me what is the conservation of energy? Anybody?
It's energy is never destroyed, it's just transferred.
Or cannot be created or destroyed?
Can't be created.
Okay, good. That's a good 8th grade answer. I like that. Good job. No, okay, good job. Okay, I'm glad AP Kim paid off for you. That's good. No, anyways, she is correct. Energy cannot be created or destroyed. Now, mathematically, what does that mean? Okay, so it means that when you hear the word conservation, that means before must equal after. So in this case here, the left side will be before. So before any type of interaction, we have any potential energy combined with any kinetic energy. This will be your starting energy during the transfer or the process. It must be converted to either final potential energy, final kinetic, and the one that we cannot get away from is heat loss. Okay? Now, there's sometimes a misunderstanding about heat. If you go ahead and pretend like you're praying and just rub your hands together really fast. Okay, do you feel that heat? Now, Mr. Johnson, if you could devise a way somehow to capture that heat and make it be able to do work, like turn a turbine to make electricity, if you could do that, it would be Isaac Newton, Einstein, Cole Johnson. If you could do that, okay, that's a big if, right? Okay, now, I'm not saying you can't, but if we could somehow reduce or minimize the heat loss, we'll be in good shape. Now, analogy. How is this analogy? Let's say it's a Friday night and you want to go to the mall. Not Carson Mall, but let's say like Meadowwood Mall, a bigger mall, okay? And your mom gives you $100, Cole. So that $100, that's all the money you have to spend. Okay. Now, when you go to different stores, like maybe Forever 21, or you go to Shields, you go to Legends, you go wherever, the Nike outlet store, you're going to spend money, right? And let's say that you decide to put your money in the bank, so you have a debit card. Okay. And what bank do you have? Do you have a debit card?
Bank of America.
Okay, Bank of America. Okay, but instead you go to U.S. Bank teller, and you go to U.S. Bank and you do the exchange. You get $20 out, but also there's a $2 service charge. That would be considered heat. That's the heat loss. Even though you got your money, there's a loss due to heat. Okay. So anyways, a couple of things here. Here's the pendulum. And so right now, let me go over here, and I'll start over here. So with the pendulum in this position right here, is this all potential or all kinetic energy? Okay, so up there, UO is all potential energy. Now, what's KO? Should be 0 because it's not moving. Now, as I let go here, it goes from potential to kinetic, back to potential, kinetic, potential, kinetic, potential. Now, what happens after each swing? Is it going to the same level, or is it getting smaller and smaller? Okay, so is energy being destroyed, or is it going somewhere else? To where? It's going to heat. Ooh. Now, heat is unusable energy. It doesn't mean it's destroyed. It means that it cannot be used to do work. All right? So eventually, this will come to rest. Now, over here, I'll go ahead and do this here, and it's going back and forth. You stop this. Going back and forth. You touch it very. Okay, I think now these both have these have a battery in it. So there's a electromagnet which provides a magnetic force which counters friction. That's why this will keep on going until the battery runs out. Okay. But eventually it will come to rest. Okay. All right, looking over here. So each subsequent swing, what happens to the we call it the pendulum? It gets smaller and smaller.
Yeah.
Okay. Now, however, on the first swing, is it pretty close? Is there minimal? Let's say I'm going to drop it from right here. Is it almost to my face? Mm-hmm. Just a little bit of heat loss, right? Now, if there was no heat loss, should it come back to where I started from? Mm-hmm. Yeah, exactly. Now, did I show the video of the girl leaning forward, hit her in the face? Okay, so if you shorten the distance, or if I give it some push like that, yeah, that. Okay, so in that case, I gave it some kinetic energy, therefore it went further than it was supposed to go. All right, so the analysis is that we're going to do this lab over here. What we want to do is that we're going to, as a group, we'll do this as a group here, and Mr. Kobe is going to volunteer to take data for us as a group here in the first part. But not yet, but what's going to happen is that we're going to release it, and we're going to try to calculate the velocity at the bottom. We're going to try to go back and forth and try to determine any energy loss due to heat. That will be the main goal here. Okay? So, theoretical part. Okay, we have to kind of, we're getting past your 5 minutes, right?
Yeah, 5 minutes.
Okay, so we have to kind of tighten it down. All right, so 44 part A, here's what we got going on here. So when the pendulum starts from here, it is all potential energy, right? Okay. So we do that, we have potential energy, so it'll be mass of the pendulum times G times HO, which is the initial starting height, okay? And we're starting from rest, right? So this will be 0, okay? Equals, now, at the bottom here, what's the potential energy here? Should be 0, okay? Good, it should be 0, okay? And it should be all kinetic energy, right? Now, there also should be some heat loss as well. Is that true? Okay, so there is some heat loss, okay? Now, here's a problem here. Okay, so if this is like, okay, let's say this is like H right here. If I bring it up here, did it move some distance vertically? Okay, but sometimes it's hard to measure this distance here. So we have to do some trig. Okay? So with that trig, let's take a look at that and see how we can measure this HO much better. Now, if I go like this, is there an angle displacement up there?
Yes.
Okay, from the vertical? Okay. So what we do here is that, here's my pendulum in its original state. Here's the mass. This is length L. Okay. So I'm going to displace the pendulum. Okay. We're going to move it up to here, let's say right here. So this is new position, and here's the string here. This is still L right here, right? That's still L. Okay. Now, you don't have to write this down because we have videotape. Okay. So now, in reality, this is really delta H right here, but this is hard to measure. Okay, but we can measure this angle theta right here. Okay. Now, when I do that, let's go ahead and take a look at this here. Let's kind of go like this here. Okay. So if I do that, if this is theta here, is theta here also?
Yes.
Okay. So we have theta here as well. Okay. So here's theta here. So this is L. Now, if I am standing right here, that's my perspective. Okay. And if I was to, let me use a different, I'll use purple here. Take a look at this triangle right here. Okay, do you see the triangle in purple?
Mm-hmm.
Okay, now if I'm here, what is this side here? Is this sine or cosine here? Cosine, yeah. This is L cosine of theta right here. Okay, and what's this side over here? Well, we're kind of in a hurry because of VBOT. Okay, so it's L sine of theta. Now, how can I measure delta H here? Would it be L minus this? Would that be delta H? Okay, good. So H, or my starting height HO, is simply whatever the length of the pendulum is, which would be from here to about the center here. That would be L minus L cosine of theta. L cosine of theta. So now I have HO, I can factor out the L, and what I have here is 1 minus cosine of theta, and that will be the actual starting height. Make sure we're in degrees, not radians. Okay, that's our starting height. So now we go up here. This becomes mg. Now we have your L, 1 minus cosine of theta right here, equals 1/2 mv squared. Okay. Now theoretically, if I release this from here and it goes to here, should all the energy be transferred to kinetic energy?
Yes.
If there was no heat loss. So all of this should go to here. But in reality, we do have heat that we have to consider. Okay, we do have to consider that part there. But anyways, if we ignore heat for right now, could I solve for the speed at the bottom? could I solve for V? Okay. So if I solve for V here, multiply both sides by 2. Okay, well first of all, what cancels out? Yeah, masses cancel out, so I can multiply both sides by 2 and then take the square root, right? So if I do that, this ends up being the theoretical velocity, 2g L 1 minus cosine of theta will equal the speed at the bottom of the ramp. So this is what we want to test here, is this idea here. Okay, hit stop.